So, welcome to the lecture. After propositional logic, equality logic, and uninterpreted functions, we came to more complex theories. First to the reals with addition, which is also called Pressburg arithmetic. And we have seen last time the Fourier-Muskin variable elimination, which is also suitable to check satisfiability of a set of constraints over the reals with addition, but we have seen that it can be exponential. So today we will look at further methods, mainly the simplex algorithm. So before we look at simplex, we will look at Gauss. At the Gauss elimination and then at the simplex method. So what is the Gauss elimination? This is probably you already all know, also from the mathematics lectures. It is about solving equalities. So if you have an equation system AX equals B, where A is a matrix and X is a vector of variables, B is a vector of constants, then this represents just a set of equations. For example, the first line, just that I just write out A11 times X1 plus A1K times XK equals B1. This is the first row. So for each row we have an equation, and we can solve this equation system by just bringing this matrix to a triangular form. How do we do this? And that we had already in the basic lectures. This is using certain transformations. Which transformations do we use? Yeah, if you should solve it, how would you do this?
Yeah, you do line transformations and add or subtract. The what's it called? The most important part of the equation you want to solve to eliminate it.
So I can have certain transformation steps on this matrix. First, I may multiply a row by a constant factor. Thereby, I do not change the equality itself. And I may add or subtract a row from another row. Since both sides are equal, by adding or subtracting, I also do not change the equalities. What does it mean if I have two rows and I add one row to the other and I get the empty row? With the empty, I mean the zero row. What does it mean? Exactly, they were linearly dependent, so that means that I have one variable free. Yeah, my constraint system does not restrict all the variables. So let us look how we do this. So we can, for each row, if it is in this matrix form, for each row, since it is linear, I can express one of the variables on the left-hand side and put the others on the right-hand side. And I can use this to eliminate variables. So, for example, if I have this equation system, then I will just use this right-hand notation here as a shortcut for this equation system, where this part is the matrix and this part is the right-hand side. So if it is AX equals B, then this is just A and B in a short notation. So, and now I would like to bring this matrix A to a triangular form. So I start with the bottom left element, and to get this element to 0, I have the choice. I could take both rows. In this example, row 1 is taken. So this is our third row, where this element should be 0. So I have to multiply the first row by 4 to get the same constant. And if I multiply this whole row, I get this value. And now I add up minus 4 row 1 to R3, and then I get this line. So let us check short. 4 minus 4 times 1 is 0, minus 1 minus 4 times 2 is minus 9, minus 8 minus 4 times 1 is minus 12, and 9 minus 4 times 6 is minus 15. So how to continue? Now I have here 1, 0, but I would like to have also these two elements to be 0. Let us continue with this one, the minus 2. So the second row starts with minus 2. I cannot take the last row now because the coefficient in the same row is 0, so I have to take the first row and I have to multiply it by 2 in order to get a sum 0. So if I multiply the first row by 2, I get 2. The second element is 2 times 2 is 4. The third is 2 times 1 is 1. And 2 times 6 is 12. And now I can add up these rows and I get a 0 here. So minus 2 plus 2 is 0. 3 plus 4 is 7. 4 plus 2 is 6, and so on. One element is left, the minus 9. So I take the third row. And to get this to 0, I can choose between these two. But if I take the first row, then I will get here again a non-zero element. So I will take the second one, and the factor with which I have to multiply is 9/7. Then I get this row, and if I add them up, then I get a triangular form. What is it good for? How do I get now the solution?
I can just see the result for the last variable, and then I can plug it in the second one.
Exactly. So this equation, the last equation, corresponds to this times the third variable equals this one. So the first variable is, the third variable is minus 1. So this row corresponds to minus 37x3 equals 37. So x3 must be minus 1. The second row corresponds to 7 times x2 plus 6 times x3 equals 15, but now x3 is minus 1, so I can plug it in, and then I get the value 3 for the second variable, and similarly I can solve it for the first variable. So we have here a very nice method, works fast, so why not to use it in general for Pressburg arithmetic? Yeah, what is the problem? What can I solve with this method, with the Gauss elimination method? Only equations. So, but in general, I have also inequations. And to solve also problems with inequations, we take the simplex method. Basically, the simplex method is also exponential. I already said it last time. There are also polynomial methods, but in practice, simplex still works better. That's why it is used for optimization also in industry and also in academic areas more often than other methods. Simplex, as I said, basically is an optimization procedure. So if you have a set of constraints, what we already know now, x is less or equal b, the x is non-negative, then under this condition we can maximize or minimize a certain function, cx. So the function is also linear. In this lecture, we are only interested in satisfiability checking. So we do not need the optimization part. So what we will deal with is the so-called general simplex. If for those of you who know the complete simplex procedure, this is basically the first part of the simplex, the phase 1. So how does it work? We have these inequations. Note that we do not have strict inequations here. They can be handled. We can talk about it if we know the procedure, how to extend it such that we can also handle strict inequations. So A is, let's say, an n times n coefficient matrix. These variables we will use in the following. So n is the dimension of the variable, so the state space, and m is the number of constraints encoded by the system. And the first step is we will convert it to the general form. So we will make, again, equations from the inequations, and we allow additionally bounds on some variables. So anyone an idea how I can transform inequalities to equalities where I allow to introduce new variables? So if I have let's say B even, and I would like to have AX equals 0, and I might add fresh variables. How can I do this?
For each row, I add another variable, and I just say the sum that's in A plus this variable.
Okay, let's say minus.
Or minus, and then it's equal to 0,
Mm-hmm.
and then I say F is lower or equal than E.
Exactly.
Yeah.
So the difference to the 0 value is encoded in auxiliary variables F. They are called additional variables or also dependent variables. If you have this inequation system encodes you a sum. Let's encode the sum by, okay, I just write it out. So for each assignment of values to the variables, this term V has the value, let's say B. V. And now, basically what I say is I transform it to express that the distance between V and the 0 value, between V and 0 is less or equal B. So if I have this term, or let's say V, if I have a certain value V minus S, this is the distance, equals 0, and V is less or equal B. So you see for a certain value, the value of this S, the slack variable, will be exactly the value of this sum. That means it encodes the distance to 0. And that's why I can just, if I subtract it from the expression, then I directly can put just bounds on the distance of the expressions to 0. So what I have now, I replace each inequation by an equation minus a new fresh variable which does not appear in the system yet, and I put the constraints on these new fresh variables. Remember, we do not have strict inequalities, and these new variables called additional or dependent variables. So what do I do if I have this inequation? The term x plus y, its value will be stored in the new variable s. So x plus y minus s1 equals 0. Note that this equation is exactly s1 equals x plus y. Yeah, so basically this term stores the value of this sum, and I make a new constraint that this new variable satisfies the bounds. This is just a trick to make equations, inequalities to equalities. Basically, nothing changes. So what do we do if we convert this system to the general form? For each of these terms, I introduce a new variable, S1, S2, and S3. I say that the term minus its variable equals 0. So for the first line, x plus y minus S1 equals 0. And now I have to store these bounds, so I say that S1 is larger or equal to. For the second row, similarly, 2x minus y minus S2 equals 0, and S2 is larger or equal to 0. And the third is the same. So what do I have from it? Now I have a normal for my system where I can work with equalities and just with bounds. These inequalities, if I go back this here, each of them corresponds to a half space. I have a picture for it here on the next slide. So if you look at this equation system, then x plus y larger or equal to is just this half space where this is the norm showing outside of the half space. So this line defines this half of the room. And for the other ones, I have also such half spaces. This is the half space for minus x plus 2y larger equals 0, and this one for the last one. And the common set, which set of points which satisfy all three constraints, is the intersection of these half spaces. This is the gray area. So this is the case that linear inequality constraints, geometrically seen, always define convex polyhedra. Polyhedra is called the intersection of half spaces, and if they are called, then we call them polytopes. And what is the general idea of simplex is basically in the first phase, we will search for one of these vertices of this polyhedra or polytope. And in the optimization phase, it will go from vertex to vertex and find an optimum. But that we do not look at, we look only at the first phase. So our goal is to find basically one of these points. How do we do this? Firstly, we introduce a new notation for this equality system. If you look at this equality system with the bounds on the new variables, then we can put them into this matrix form. That means basically that this matrix multiplied with this column vector equals 0. And I have additionally these bounds. So you see that here on the right-hand side, since we introduced for each equation an own new variable, this is just minus the identity matrix, so we can let it away. And to remember which variables were here, we write them here on the left. So we use this notation to represent the equation system where each row basically encodes that S1 equals, in this case, x plus y. The second row encodes that S2 equals 2x minus y, and so on. S3 is minus x plus 2y. In this notation, we will modify this tableau. We will modify the values, but the structure, the size of the matrix will remain constant. And we distinguish between these variables, which are called non-basic, and these variables, which are called basic. And we will use B for the set of basic variables and N for the set of non-basic variables. And since due to construction, it is always the case that at the very beginning, the basic variables are the additional variables, which you introduced newly to convert the inequations into equations. And this is just a different notation for the system that the basic variables equal the weighted sum of the non-basic variables. Okay. What we do now, the following. The intuitive work, how simplex works intuitively is the following. If I have some bounds, yeah, on the basic variables. The basic variables are initially on the left-hand side, but I will pivot, I will modify this tableau, and they may also come to the non-basic variable set. The goal is that all of these variables satisfy their bounds. If it is the case, so I will assign a value to each of these variables, which is initially 0, and then we modify this value until either all of these variables are within their bounds, or I find out that there cannot be any solution. And there will be some invariance on this matrix, namely that the non-basic variables always satisfy their bounds, So if there are some variables which do not satisfy their bounds, then they are in the set of basic variables. And if one of these basic variables, let's say S1, does not satisfy its bound, then I will search for some of the non-basic variables. I will just select one such that I can modify the value of, let's say, S1. Assume that S1 is larger than its lower bound. Then that means that I must make the value of S1 smaller in order to satisfy its, larger than its upper bound. So I must make the value of S1 smaller in order to satisfy its bounds. If I make it smaller, since this is an equation such that the equation still holds after the modified value, I must also change the right-hand side. And basically, I could take a combination of the variables x and y, could modify both values such that the equation holds. But the basic idea of simplex, why it works very well, is that I just choose one. All the change which I make to S1, I will compensate by either changing the value of x or y, but not both in one step. However, this may, of course, lead to violating the bound, let's say, of x. If I reduce the value of S1 and I reduce the value of x also, that the equation holds. Then it might be that now x violates its lower bound if this coefficient is positive. Therefore, I modify my tableau and I change x and S1 because now I know that S1 is within its bounds. So I put it to the non-basic variables, and if x is outside its bounds, then it must be under the basic variables. And in order to not to get to these loops, by in the next step, for example, changing the value of x and taking S1 as compensation, we will take only those non-basic variables which are not yet at their bounds. That means for which it does not hold that if I modify them with epsilon, then they already violate their bounds. And with an additional condition, which we will look at Blend's rule, is this method complete. So let us now look after this idea in detail. So we have this tableau, and we start with an assignment that assigns a value to each of the variables. And initially these values are 0 for all original variables and also the select variables, the additional variables. And we will modify this tableau, but we will maintain two invariants. First, the equation holds all the time. That's why if I modify the value of a basic variable here, then I also must change some of the values of the non-basic variables such that these equations still hold. So this is the first invariant. And the second is that all non-basic variables satisfy their bounds. So if I change the value of a non-basic variable and thereby it might violate its bounds, then I have to remove it. So we start with this initial value 0 for all variables. Does this satisfy these invariants? Of course, yes, because if I assign to each variable the value 0, then AX is of course 0. Firstly, and secondly, I must assure that all non-basic variables satisfy their bounds. Why do I know that all non-basic variables satisfy their bounds with the value 0? Yeah, these are the original problem variables. They have no bounds. Only the additional variables have bounds, and they are initially in the basic variable set. So these non-basic variables are the original variables, and they satisfy their bounds trivially because they do not have any. So initially the invariants hold, and now we will make changes, and we will show that these invariants also remain satisfied. So now I check. Are the bounds of all basic variables satisfied by the current assignment? If this is the case, then I know that the non-basic variables satisfy them by the invariant, so I am done. I have a valuation which satisfies all bounds. If not, then we do something which is called pivoting. Pivoting searches for a basic variable xi that violates its bounds, And in the following, let us assume that it satisfies its lower bound. The upper bound case is completely analogous. So now we have this variable xi. This violates its lower bound, so I will have to increase its value in order to satisfy the inequation. So I will search here for another variable, a non-basic variable xj. Oh. How did I do this? Sorry. I will search for xj such that either this coefficient aij is larger than 0. If this is the case, I want to make xi larger. So if this coefficient is positive, then I also have to increase the value of xj in order to keep the equation valid. So that's why in this case, the value of xj must not be at its upper bound. Because if it is at its upper bound and I will increase it, then the whole thing I will have to decrease with the same value, at least with the same value again. So such variables, we say that they are not suited for pivoting. So in this case, I search a variable xj whose value is strictly less than its upper bound. And in case this coefficient is negative, if I want to increase xi and this coefficient is negative, then I will have to decrease xj in order to keep the equation. So in this case, xj, the value of xj must be strictly larger than its lower bound. And such a variable we call suitable for pivoting. Now, if we do not find any suitable variable, then we return unsatisfiable. Why is it the case? So I go back one slide because there is this tableau. So assume I have this row and I call just now the left-hand side fi equals I do not want to use x and s because they suggest that these are original and additional variables. This is not the case. So I will just take v. A variable equals a sum of let's say w. And now this variable, the value is too small, so I want to increase it, but none of these variables are suited. That means either their coefficient is positive and they are already at their upper bound, or its coefficient is negative and they are already at their lower bound. Why is it the case that then this equation system is not satisfiable?
I can't increase any of the AW, so I can't increase the whole sum.
Exactly. So if I look at the value of this sum, for different values for the variables, this sum might have different values. But I have already taken the largest value which I am allowed to take due to the inequations, due to the upper bounds. So there is no way of increasing the value of this sum. That means we have found a reformulation of the problem which proves that these bounds together with this equation system are not satisfiable. So in this case, we can return answered. Otherwise, if there is one, then we just take one and we reformulate the problem. So assume that we have here on the left-hand side the variable which violates its bound, and we have So we reformulate the problem. This is the row. xi is the variable which is outside of its bound. This is the right-hand side, and xj is the variable which we take for pivoting. So we just reformulate the problem that xj comes to the left-hand side just by making minus this term, multiplying with minus the coefficient. And then I get a new form where xj is on the left-hand side. I can always do it because the term is linear. And now I can use this equation to pivot. That means this was the row describing the first equation, and I changed the row to the second equation. But now, here on the left-hand side, I had xi, and here I had xj. Now, if I reformulate this problem, then this equation corresponds to xj equals the sum where here I have xi. That means the both are changed in the new equation. And this is the pivoting step where so that a picture will come. So if I have here xi, xj, and here was the coefficient, then I will just change them and modify this row here from the old one to the new one. It is just reformulating an inequation, but what it makes efficient is that I have now the computation rules how to do this. So I do not have to reformulate all the time. I can just compute the new coefficients from the old one algorithmically. Okay, now the problem is that I pivoted these two. So if I have another row, I have here somewhere another row for another variable, x, let's say. Then previously, this coefficient here was in the sum for xi. Now I pivoted, so I must replace this component by the new expression of xi. So basically, I have to add up this row to this row instead of this coefficient. In detail, this looks like the following. For all other rows, we replace xj with its equivalent. So with the row for xj, and we also have to take care that the assignment now is changed. We increased the value of the variable which was its bound. We pulled it to its bound. So this is the difference which was missing. We had the variable xi. Li is the lower bound. This was the old value of xi, and this is the difference. And I have to increase the value of xi with this difference. To do so, I compensate it with the value of xj. So I have to divide it by the coefficient of xj to get exactly this value, which I changed the left-hand side of the old equation. So again, if I have here, the old equation was xi equals a sum plus aij xj plus some more. So I have to increase the value of xi from alpha of xi. It will be changed to li. I increase its value such that it exactly satisfies the lower bound. Now on the right-hand side, I must change the value of the right-hand side exactly by this value, and this value is then li minus alpha of xi. This is the difference for xi. And now I put all this difference into this term. That means if I change the value of this term by theta, the change of the value divided by aij and multiply it by aij, then I get exactly the term. Yeah, so this theta gives me the exact value with which I must change the value of xj such that I compensate this change on the right-hand side. Okay, this is for the pivoting variables. And since now xj might violate its bounds, we pivot the rows and columns of xi, xj. And now the other basic dependent variables might also be influenced by this pivoting, so I have to update also their values. Let us look at an example. We have this constraint system from the beginning, and these are our bounds. Initially, we said that all variables have the value 0. X is 0, y is 0. That means all the slack variables are also 0 according to the equations. And since S1, for example, must be larger or equal to, this bound is violated. S2 satisfies its bound, but S3 is also violated. So I have the possibility to choose either S1 or S3 for pivoting, and we choose in this example S1. Now we have to search for a variable that is suited for pivoting. For S1, both variables are suited because their coefficient is not 0. So they indeed put a certain part to this sum on the right-hand side. And they have no bounds, so I can pull them as I like. Let us change now, choose now x. So I want to pivot with S1 and x. The first row means S1 equals x plus y. Now I can reformulate it in putting x to the left-hand side and S1 to the right-hand side, and I get this equation. And I modify this tableau such that now I have x here, S1 here, and here I have these coefficients. And since instead of x now I have S1, I have also modified the other rows. Previously I had S2 equals 2x plus y. And now I have to replace x by this term. 2 times S1 minus y. If I reformulate it, I get 2S1 minus 3y. I do this for the third row also, and I get this new constraint system. I pivoted x and S1, and I modified the other rows accordingly such that their value do not change. By this pivoting, the only difference is, until now, we did not change any values yet, the equations hold. The only difference is that now the bound of x currently is satisfied, but S1 might violate this bound. So we have to change the assignments such that all the non-basic variables satisfy the bound. Previously, the values were 0. Now I wanted to pull S1 into its bound, and the low bound is 2. So I will have to increase the value of S1 by 2. This is theta. 2, and if I want to take x for compensation, its coefficient was 1. That means I can change S1 and x in the same manner. If I change the value of S1 with a delta, then I also have to change the value of x with delta to keep the equation, because the coefficient is 1. So that means that also the value of x will be changed by the same value too. So the value of S1 becomes 2, and also the value of x becomes 2, and this equation is satisfied now. And I have to update also the values of the remaining variables here, because they are affected now by the change of this value of S1. So I compute also S2, which is now 2 times S1, that means 4, minus 3 times y is 0, so the value of S2 will be 4, and the value of S3 accordingly minus 3. Now I'm a bit better, because S1 satisfies its bound, S2 also, but I have a problem still with S3, which is minus 2, so it is below its lower bound. Then I do the same. I take S3 for pivoting, and again I search for a variable which is suited for pivoting. S3 is below its lower bound, so I have to increase its value. If I would take S1, its coefficient is negative. That means if I increase the value of S3, I have to decrease the value of S1, but it is already on its lower bound. That means I cannot take it. I can take Y. Y doesn't have any bounds, and its coefficient is not 0, so y is suited for pivoting. And I have to increase the value of S3 by, current value is minus 2, lower bound is 1, so by 3. And the coefficient of y is 3. That means I have to increase the value of y by 1, then the equation holds. And now if I pivot for the same manner with S3 and y, then the resulting tableau will look like this, and the assignment will look like this. And I check again. S1 has the value 2, which is at its lower bound. It is fine. S2 has the value 1. This satisfies also the lower bound. And S3 has the value 1, which also satisfies the bound. So all variables satisfy their bounds, and I have found a solution. In the other case, if I find a row where all non-basic variables are at their bounds and I cannot use them for pivoting, can it be the case that one of them are original variables? So now assume that I have a tableau, and I have here a row with xi, and none of the columns let's say x1 prime to xn prime, none of these are suited for pivoting. Can it be that one of x1 prime to xn prime are original problem variables? Not additional variables, but one of them is original. Can it happen?
No, because they have no bounds. Always choose them.
Exactly. So in this case, if the problem is unsatisfiable, then all of them are additional variables. So if I find out then that the problem is unsatisfiable, then basically I get a conflict with respect to the additional variables. That means it corresponds to a set of inequations. Yeah, because these bounds, which are now n plus 1 bounds, which are involved at most n plus 1, some of the coefficients might also be 0. These n plus 1 variables correspond to my inequations. I added them in order to formulate the equations to inequations. So if I find such an unsatisfiable problem, and I would like to generate a reason for the unsatisfiability, that means this explanation in the SMT approach, how could I get such a subset of the original constraints which are together unsatisfiable? A minimal infeasible subset, which we had last time. So now the problem is that this, I found out that the problem is unsatisfiable, and if I would like to use this approach in SMT solving, then I must satisfy these 3 requirements that we had: the incrementality, generating minimal infeasible subsets, and perhaps backtracking. And one of them is generating this minimal infeasible subset. So now I know that the problem is unsatisfiable, and originally I had m inequations, and I would like to give back a subset of these inequations which are already unsatisfiable, as small as possible. So how can I generate such a subset? We were already at the point that all of these variables which are involved, whose coefficient is not 0, are additional variables. That means they encode basically an inequation. which of the inequations do I have to consider in order to keep this row conflicting? All of them. Yes, so each of them corresponds to an inequation. If I take xi, this corresponds to some, so I now rename them because we know that they are slack variables. So I call them S without index now, and this I call S1 prime to, or S1 to Sn. S corresponds to one inequation. I had some row originally for S1, X1, Si, Xi equals less or equal Bs, sorry. This is the inequation for S, because I introduced S to reformulate it to an equation. So if S, the bound of S cannot be satisfied, that means that this inequation cannot be satisfied. But only if all of these bounds are present. That means if I collect the inequation which corresponds to S, and I collect the inequation corresponding to all of these bounds, whose coefficient here is not 0, then these inequations together are unsatisfiable. If I would have started just with that set, I would get the same conflict. Yeah, so this way I can just get for free from the resulting tableau a reason for unsatisfiability. Okay. A last point is completeness. So if we apply simplex, now we have looked at an example and we have seen that it terminated. We got a result after a finite number of steps. The question is it always the case? Can it be that we pivot two variables, xi and xj, and then they continue, and at the later stage, we undo this? That means we will pivot xj with xi. And this way we can enter a cycle. That means that it would never terminate. If we do not do this, then it always terminates. This is clear. For non-termination, you always need a loop. We have only finitely many possibilities for pivoting, and if we do not undo a pivoting once, then we terminate after a finite number of steps. But here we can get the cycle. So is it possible to get into such a cycle? What do you think? It is not trivial, but we can have an easy example, easy explanation. This is not possible directly after each other. Now let us start with that. So it is not possible directly after each other. If I pivot with xi and xj, then directly in the next step, I will not pivot back. What is the reason? If I pivot back, then xi must be suitable for xj. This is not the case. Why? First, I pivoted, I must change the value of xi, and I change it such that the remaining part is put in xj and xi is exactly at the bound. I do not change its value too much, only as much as I need to satisfy the bound. So let's say, assume that xj, sorry, what was the, that xi violated its lower bound. So I have xi and xj. Then xj was, the value was too small, so I had to increase it. Assume without restrictions that the coefficient was positive, then I also have to increase the value of sj. And now xi is exactly at its lower bound. If xj afterwards have to be pivoted, that means it violates its bound. If I increase it, that means that it got above its upper bound. If I got above its upper bound, in the next pivoting, I will have to push it back. So I must make it smaller. But I cannot make xi smaller because it is exactly at its lower bound. So it will not be suited for pivoting. Therefore, it is not possible to enter this cycle directly, one after the other. But there might be longer cycles where it can happen, and there is blend rule. It's a very simple rule which assures termination. And this says that if I have a choice to choose a variable, then I choose it according to a variable order. It means if I have to choose a basic variable, then I will choose the first one in this order that violates its bounds. And also if I choose a variable for pivoting, then I will take the first non-basic variable that is suited in this order. And then it will be complete. So here you can see a summary of the general simplex method. That means we first transform the problem into a general form by adding new slack variables. Then we have a tableau with two invariants that the equation holds and the non-basic variables satisfy their bounds. And then as long as basic variables violate their bounds, we do pivoting. If all basic variables satisfy their bounds, then the problem is satisfiable. And if we have a bound violation but no suitable variable, then the problem is unsatisfiable. Otherwise, we can still pivot and continue, and Blend's rule in this application assures that we always terminate. So it is a complete procedure. I'm sorry, taking time from the exercise, but I just didn't want to stop short before the end. So, and next time we will look short how we can plug in this simplex procedure into SLC solving, and then we will also look how we can extend it to deal with integer valued variables. Thank you.